Alright, so the mic has 2 bars, so I assume it's working. Okay, that's a good sign. I wonder if I can increase the volume. So I realized it wasn't recorded last time, not sure why. They say the battery may be the culprit, but I don't know. Now this is as loud as it can be. Okay, let's hope it's being recorded. So, we talked about the Fourier transform last time, and then we talked about the analysis and synthesis equations, and we start talking about a number of interesting properties of Fourier transforms. And the one we started discussing was the convolution property. That's a very important property of Fourier transforms. It says that if I take the convolution of 2 signals, okay, how about now? Okay, needs to be tickled a little bit. Okay, so if you take the convolution of 2 signals in time, what happens in the frequency domain is that you're really multiplying their Fourier transforms. Okay? So if you have any kind of dislike for the convolution, the way to save you from doing a convolution is to go to the frequency domain where it just becomes a multiplication, if multiplication is more agreeable to you than convolution. But then the price you pay is you have to go to the frequency domain. And then you have to evaluate these integrals. But there are, once you know the Fourier transforms of a few basic functions, you can actually construct, using linearity properties and other properties of Fourier transforms, you can construct the Fourier transform of a more complicated signal from the Fourier transforms of simpler signals. So that way you don't have to evaluate these integrals involved in the analysis equation to go to the frequency domain. So let's talk about why this is true. This is actually fairly straightforward to derive. So let's first recall what this meant. It meant that we are doing an integral of x1 of tau multiplied with x2 of t minus tau, right? With respect to tau, from negative infinity to infinity. So that's something we discussed in great detail. You flip and drag one, keep the other same, and then the time argument becomes tau, and then we integrate over tau, so tau disappears. Now we're going to take the Fourier transform of this, right? So what results from this integration is a function of time. Tau disappears once we integrate over tau, so what remains is a function of t. So to find the Fourier transform of this, we apply the analysis equation, which means we multiply this with e to the negative j omega t and integrate over t. Okay? So essentially when you combine the two, you have 2 integrations, one over t, the other over tau. And I can always swap the order of those integrations, and if I do that, so if I switch the order, so I have double integrations. I'm going to stop writing negative infinity positive infinity, that's obvious. So let's first do the integration with respect to t instead of tau, because that way I can leave tau, x1 of tau, which depends only on tau, out of the inner integral. So the inner integration will run over t, right? dt, and then we'll do d tau. Okay, so what I have to put inside this is x2 of t minus tau and e to the negative j omega t, because those guys are the only things that depend on t. x1 doesn't, so I took x1 out of the inner integral. But if you look at this expression, that looks just like the Fourier transform of x2, right? Except that it's not x2 alone, it's x2 of t minus tau. So it's a shifted x2, right? So what did we learn about the shifting, time shift property for Fourier transform? it amounts to, it does little really to the Fourier transform. It just multiplies it with e to the negative j omega times the amount of time shift. Okay? So this really can be expressed in terms of x2 of omega using the time shift properties. E to the negative j omega tau, because tau is the amount of shift, x2 omega. Okay, so this inner integral is equal to that from the time shift property. Okay, so that makes our life a little easier because now we have x2 of omega that doesn't depend on tau. I can take that out of the integral. What remains is x1 of tau. This guy is still there. We have to take care of it. E to the negative j omega tau d tau. But x2 of omega has nothing to do with tau, so I can take that out. But of course, you recognize this term here that really is the Fourier transform of x1, right? So what I have is x1 omega, x2 omega, which is the proof. Fourier transform is x1 omega, x2 omega. So that really is a remarkable property for those of you guys who don't like doing convolutions. That gives you a way out. Just go to the frequency domain, life is peaceful there. Okay, so let's see an example. We already saw an example last time. I gave you a triangle function, and I said you have two choices. You can either apply directly the analysis equation to find this Fourier transform, but that's going to be painful because you have to do integration by parts and all of that. Or you can see the triangle as the convolution of a rectangular pulse with itself. And now you can use this convolution property. That means really squaring the sinc function, which is the Fourier transform of a single rectangle. Right? So that's what we did. Here's another example that saves you from the trouble of doing a convolution. So that's our second example, really, adding to the one from last time. But I'm going to call it example 1, because today it's example 1. So I give you two signals. x1 of t is e to the negative at times u of t. Okay? So it's an exponential thing like this. And a is positive, so that it decays. And x2 of t is e to the negative bt u of t. Again, b is positive, so that's also a decaying function. And I'm going to add a condition that a and b are different things. Okay, and you'll see in a few minutes why that makes our life easier if working this example out. And I ask you, what is x1 star x2 of t? Okay, can you do this? Well, you can. I mean, you just have to, both functions has to stay put here, there has to be flipped and dragged, and then you look at their product, you integrate their product, and whatever. It's not a pleasant operation. So let's see if it's any easier to do this in the Fourier domain, in the frequency domain. Well, one thing is already easier because we worked on these examples last time and we saw the Fourier transforms of those. Does anybody remember the Fourier transform of this guy? Good, 1 over 8 plus j omega. And in obtaining this expression, it was critical that a be positive because otherwise the integral involved in the Fourier transform does not converge, right? Similarly, x2 of omega is 1 over b plus j omega, right? Because b is positive. So I know that x1 convolution with x2 has a Fourier transform that is the product of these. 1 over a plus j omega, b plus j omega, when I multiply them. So to find the convolution without really doing the convolution, all I would have to do would be to go back to the time domain from this expression. what is the inverse Fourier transform of this guy here. Okay? Now, this may not be an easy task if you directly apply the synthesis equation to this, because that requires an integral, you have omega squares, all kinds of things in there. But we can make things a lot simpler if we use what is called a partial fraction expansion. Have you ever heard of that? No? Yes? Okay, some have, some haven't. It's not a big deal. We're going to keep seeing this in this course. It will simplify doing inverse transforms, whether it be Fourier or some of the transforms we'll study later. Partial fraction expansion will come to the rescue. The idea is simple. If you have a product like this, try to write this as some coefficient a by a plus j omega plus another coefficient b by b plus j omega, where a and b, the capital A and capital B coefficients, are to be determined, right? So basically the question is, can I write this highlighted thing here in this form? Well, we can investigate whether that's possible or not. If I combine these terms, I can write this as a times b plus k omega plus b times little a plus k omega, right? That goes in the numerator. And the denominator is the product of a plus k omega and b plus k omega, right? So for this expansion to match what we started out with, the numerator has to be equal to 1, right? Only then they will match. So numerator is, if I separate out the real and complex terms, I'm going to get AB plus BA plus J times A plus B omega. Do you agree to this? I just rearranged what I see in the numerator, right? And I want this to be equal to be 1, because the numerator up here is 1. Okay? If I can find capital A and capital B that makes this expression equal to 1, then I'm done. I've expanded my product in the form of a sum. Okay? Is it possible? Well, this being 1 means this is equal to 1, right? And this must be 0, because I don't see any omega on the right hand side. I don't see anything complex either, right? So I have two equations and two unknowns. AB plus BA is 1. A plus B is 0. This one allows me to get rid of B, because B has to be negative A. I can go back and substitute B back in here, and that way I get A little b minus A little a, which is A b minus A, equal to 1. Okay, so that means A is equal to 1 over B minus A, and B is equal to negative 1 over B minus A. A and B were the givens, so we were looking for big A and big B, right? And that is the solution. Now, you see why this is kind of critical. We assume that little a and little b are different things, because if they were the same, our partial fraction expansion would have failed miserably. There would have been no solution. I mean, you can see division by 0. That basically means these two equations have no solution, right? So the problem here, of course, is if a and b are the same, the product I'm looking at is 1 over a plus j omega squared, right? How can I possibly write it as something by a plus j omega and something else by a plus j omega? Those two things will look the same, right? So I can't write something square as the coefficient times something, right? So that's why a equal to b case failed. At least you can't do the partial fraction expansion. You can do other things that we'll see later, but the partial fraction expansion will not work. All right? So what did I gain from partial fraction expansion? I made the product look prettier. I made it look like a sum, right? So now I know, using these coefficients, that the product x1 omega x2 omega is, what was the a? 1 over b minus a or a minus b? B minus a times 1 over a plus j omega. And then capital B had the opposite sign, so it's a negative. So this is our a, this is our b, okay? 1 over b plus j omega, right? Okay, so that's the benefit of the partial fraction expansion. Now things look simpler. In fact, to find the inverse Fourier transform of this, I don't have to do any integrations because I already know what the inverse Fourier transform of this is, right? This is a very basic function, exponentially decaying function multiplied by unit step, right? We know, we studied the last example, we don't have to do it every time, right? We'll just use our knowledge from the last lecture. We know that this is the Fourier transform of e to the negative at u of t, right? So if it's not clear by now, that means they'll go together. Take a mental picture of this because we're going to keep using this all over the place, okay? So similarly, this term here, this guy here, goes with e to the negative bt times u of t. So that's a Fourier transform pair, okay? So knowing that, going back to the time domain is easy. I already did, right? So using the linearity property of Fourier transforms, I can just say the inverse Fourier transform, which I know is the convolution of x1, x2, is 1 over b minus a times e to the negative at. And I have the same coefficient with the opposite sign. And both of them have factors u of t, which I factor out. So I can write it in this form, right? And there you go. You've done a convolution without doing a convolution, right? You've used the multiplication property in the frequency domain to evaluate the convolution without actually needing to do it. Any questions on this? Okay, so I think that's good enough for the convolution property. It just becomes multiplication and much more agreeable in the frequency domain. Alright, so this is something I barely touched upon last time. The derivative properties of the Fourier transform. From now on, I'm just going to write ft for Fourier transform, or I write less. Okay? It's fairly easy to derive this. All you have to do is go back to the analysis and synthesis equations. If I take the derivative of both sides of the analysis equation, or let's start with the synthesis equation. Yeah, so let's take the derivative of both sides of the synthesis equation with respect to t. Okay, so I'm going to try to squeeze this in here, right? So dx of t dt, according to this expression, is 1 over 2 pi integral. Nothing happens to x of omega because it doesn't depend on t. The only thing that depends on t here is this, right? And what's the derivative of that with respect to time? J omega times e to the j omega t omega, right? All agree with this? So this is a foreign object here. Doesn't belong here. If I take it out of there, wait, this is, no, wait, you're taking, wait, did I mess up? Oh, no, of course, I'm not going to take it out, so that's wrong. So I'm just going to look at it all together, okay? So what I'm seeing on the right-hand side looks like a synthesis equation, right? Except that the transform x of omega is replaced with j omega times x of omega. Okay? So that means dx dt in the frequency domain is j omega times x of omega. Right? So that's our first derivative property. So dx dt will give you, so if x goes with x of t goes with x of omega, if they're a Fourier transform pair, then dx dt goes with j omega times x of omega. Okay? So we can do something similar to the analysis equation. Now let's take the derivative of this with respect to omega. Dx omega, d omega. Again, same thing. The integral is almost unchanged, except that I have to take the derivative of this with respect to omega. That will give me what? A factor of minus jt, not omega. I'm taking the derivative with respect to omega. Seen from omega t is just the coefficient, right? X of t e to the negative j omega t dt. So this again looks like the analysis equation for a modified signal, negative jt times x of t. Right? So from this we conclude that negative jt x of t will have the Fourier transform dx omega d omega. Right? So fairly easy to obtain. In fact, we can use these things repeatedly, right? So what if I were interested in the second derivative of x? d square x dt. Then I would have to multiply with j omega twice, right? So you can take the kth derivative, dkx dtk. That just suggests that you will have to multiply with j omega k times. So this is nothing but a repeated application of the same rule. Will give you that. Okay. Similarly, this will give me negative jt power k times x of t, Fourier transform the kth derivative of the original Fourier transform. Okay. All right, so that's a useful property. And note also that there is sort of a duality here between these two properties. The first property at the top says that derivative in time domain amounts to multiplication with omega in the frequency domain. That's the property at the top. And the property at the bottom says derivative in the frequency domain amounts to multiplication with t in the time domain. Right? So that's kind of, those two are kind of dual to each other. But again, you have to be careful when you use these duality arguments because you have often different coefficients. Like in one case you multiply not with omega but j omega, and in the other case with negative j times t. So that's the extent of duality you can talk about. Alright? Any questions on the derivative property? Alright? So that's potentially another useful tool, because if you already know the Fourier transform of a signal, you don't have to derive the Fourier transform of the derivative separately. You just multiply with omega. Let's look at an example for this. Sure. By the way, the notes are online. It takes me a lot of time preparing those. Okay, so we might as well take advantage of those. Okay, questions? No? Welcome. Alright, so let's look at an example. Actually, not a new example, the old example. I'm going to call it example 2, but it really is example 1, because I'm going to be interested in the convolution of x with itself when x is e to the negative at u of t with a positive. Okay? Why is this sort of the same as example 1? It's actually a special case of example 1 that we did not allow. Let me go back to example 1. We have e to the negative at, e to the negative bt. I said a and b are different, right? If a and b were the same, we will get into trouble when doing the partial fraction expansion. Okay? So now, I'm taking a and b to be the same, basically. So that means the convolution of e to the at u of t with itself, right? Okay, so we again can use the convolution property. That's still correct. So that means this goes with x of omega squared. And what is x of omega? A plus j omega, right? That's it. So we're looking at 1 over a plus j omega squared. Okay? So now to find the convolution of x with itself, I have to find the inverse Fourier transform of this. Partial fraction expansion will no longer come to my rescue because there is no hope of writing this as a coefficient times the coefficient pi a plus j omega plus another coefficient pi b a plus j omega, because that's clearly something by a plus j omega. They will not match. Well, then b is 1 and the first one is. Yeah. So you can, this has no hope because it comes as a product, I mean square, right? But, you know, that's not the end of the world. Maybe there's another trick. The worst case is you bite the bullet, you do the integral or the simplest equation. But I tell you there's an easier way. And hint, usually examples follow the properties we discussed. Right? So maybe, looking at this 1 over a plus j omega squared, you can see the derivative of something with respect to omega. Something familiar and cozy and friendly. No, not that bad. That's not my definition of cozy and friendly. So can you say this is d by d omega of something pretty? The constraint is this has to look pretty enough, okay? And then you may have to add some, you know, coefficient in front of it. Yeah, what are you saying? What's your answer? So you're saying negative 1 comes in front? Negative j? Alright, is everybody in agreement with this? I'm not going to question it. Take it easy, leave it to the majority vote. So do you guys agree with this? Okay, I'm not going to do this. I trust you. We bring the air pan so that we can check this. Are you guys convinced? Everybody's happy? Okay. If it's wrong, it's not my fault. It wasn't my idea. Okay. Still some questions linger, okay? I just wrote what you guys told me, okay? So, okay, you're saying now positive? Do both agree with this? Okay, again, I'm not going to question. Okay, so it's that. So then what can I say? Well, I know that this guy here, well, first let's start with what's inside. I know the guy inside is the Fourier transform of e to the negative tu of t. So I also know that the big thing now, the derivative of this, the derivative of that, must go with, using our property, it must go with negative jt
times x of t, right? So that means I just have to multiply with negative jt e to the negative at u of t. But we have a j hiding here because of the linearity property of Fourier transforms. Scaling one thing in the time domain scales the same thing in the frequency domain, that kind of stuff. So that means we have to also multiply with j, right? So that means our convolution is this, and happily you get a negative j squared, that is 1, right? So you simply get t e to the negative at u of t.
Kind of interesting. So when you take the convolution of e to the negative at with itself, you get t times e to the negative at.
How does that compare to e to the negative at? E to the negative at looks like this, right? It starts at 1, decays. Where does t times e to the negative at start? Again, because of u, they are both 0 before 0, right?
So where do I start? 0, right? But then, so two things happen. There are two terms there that have conflicting objectives. T wants to blow up. E to the negative at wants to drop to 0 as quickly as possible, right? So it's a conflict between those two terms, right? Who wins, do you think? Exponential decay is a very strong type of decay, right? Polynomial growth is okay growth, but it's not as bad as exponential growth. So if you have polynomial growth competing with exponential decay, exponential always trumps polynomial stuff. So the decay will win because it's exponential.
I guess that's not a very mathematical expression, but so what happens is, there is a time when t thinks it's spinning, but then really you will come back and convert to 0.
Okay?
So you can also show that if you did this 3 times, and we talked about the associated distributive properties and all that for convolution, so you know that this thing makes sense. You just do it like this, that doesn't matter which order. You can in that case show, I'm not going to do it, but you can show that you get t squared by 2 times e to the negative at u of t. Okay? So now you have a somewhat more powerful growth term,
but it's still polynomial. It will still get eaten up by the exponential decay eventually.
Okay? In fact, if you do this r times, you're going to have t to the r by r, what do you call this, factorial? Yeah, it's the factor, it's not like gr, it's not like exclamation. E to the negative t, alright? If r convolution takes place.
Alright, so we couldn't do the partial fraction expansion, but the derivative property came to our rescue. So these two examples should illustrate to you that these properties are really important. They save the day for you. You don't have to do these, synthesis analysis equations, the integrations to really get the Fourier transform. You just need to know those for a few basic functions, and a lot of other things can be derived from those without evaluating integrals.
Okay. Well, I'm going a little slowly, so I need to move on. So a third property today, and we really have 4, and then we'll investigate some of the interesting implications of these properties, is the frequency shift property. And this property is what gave humankind, to use good words, the radio. We'll talk about that in a second. So if I take x of t and multiply it with e to the j omega naught t. Omega naught is some frequency. Maybe 440 hertz. That's A, right? Somebody said that last time. So basically I'm playing a single note, a single tone, right? I'm multiplying it with x, right? what happens to the Fourier transform of little x? Well, let's see. It's actually the simplest derivation ever in this course. Well, I'm applying the analysis equation to this signal, the product, right? That means I'm multiplying them with e to the negative j omega t and integrating over t, right? And the result is the Fourier transform of the product. Well, these two go together. I can merge them into one, so that becomes x of t e to the negative j omega minus omega naught t dt, right? So this looks awfully like the Fourier transform of x itself, except that instead of omega, I have omega minus omega naught, right? So that really can be written in terms of x of omega if I just replace the argument with omega minus omega naught. So this just goes in here, right? And there you go. You have the frequency shift property, x of omega minus omega 0. Okay? So, multiplying with a sinusoidal with a fixed frequency omega naught in frequency domain amounts to shifting the Fourier transform to the right by omega naught. And you should see the duality of this with the similar property we studied. You remember the shift property, right? X of t minus t0, that went with what? E to the negative j omega t naught x of omega, right? So there I'm multiplying the Fourier transform with the sinusoidal term, sinusoidal function of omega, and then that amounts to shifting the time, the signal in time. Okay? Alright? So this is also called the modulation property sometimes. Do you have any questions? No questions. Duality is a vague, slightly vague thing. It means that, you know, some property that relates the time domain to the frequency domain has an analog that relates frequency to time, right? Examples were derivative properties, right? So we observe that taking derivative in time amounts to multiplying the frequency in the frequency domain, and taking the derivative in frequency amounts to multiplying the time in the time domain. So, the operations, if you look at the analysis and synthesis equations, they are not that different, right? I mean, they are both integrals. This omega and t change roles. There's a sign flip that usually spoils the, a perfect duality where you have everything is symmetric. Alright, but I really have to move on. Okay, so frequency shift property is that. It's very simple. And why is it useful? I don't know if anybody here still listens to AM radio or to radio to begin with. Maybe in a car if you're driving. Okay, so the example is amplitude modulation, AM. Sometimes you see signs on the side of the road saying traveler information, things like that. So they are usually AM stations. It's usually used for, for music and things like that. It will be FM because it has better quality. So if it's just speech, Rush Limbaugh talking or, airport delays, that kind of stuff, AM is good enough for that level of things, right? AM. Okay, so what's happening here? So I'm speaking, and I want this to be broadcast. So the S of t is my signal, right? And so what happens in AM is very simple. We take the signal using some appropriate circuitry that can't be too complicated because radios have existed for 100 years or more. You just multiply it with a sinusoidal signal. Okay? Cosine, I'm going to say for doesn't matter, cosine omega naught t. Okay? And this omega naught is called the carrier frequency. So if the sign on the side of the road says tune into 1600 kilohertz for traveler information, that really means the carrier frequency for that particular station is 1600 kilohertz. Okay, so that's the carrier frequency. And then you get, if this signal looked slowly varying initially, right? After this modulation, this is called modulation, the multiplication by a sinusoidal, the envelope will be preserved, but it's going to have a bunch of crazy oscillations, right? It will be a really wiggly signal after the multiplication, right? And then you send this through air, okay? So, and that gets received and demodulated. We'll talk about that part, but let's for now see what happened to the signal in the frequency domain. Clear what happened in the time domain. We just multiply with cosine omega 0 t. But remember, cosine omega 0 t is, I can write it in this form, right? It's 1/2 e to the j omega 0 t plus 1/2 e to the negative j omega naught t. Alright? So basically the signal that I have here is 1/2 s of t e to the j omega naught t plus 1/2 s of t e to the negative j omega naught t. Right? So tell me please what the Fourier transform of this first term is. It's written at the top. There's a 1/2 that I have to live with, that's fine. Okay, big S, omega minus omega naught, right? What about the second term? It has another 1/2, and S omega naught, right? So basically what happened to the spectrum, to the Fourier transform? If I say spectrum, that means the Fourier transform. Okay? So what happened to the Fourier transform of S is that I took it, shifted it to the right by omega naught, shifted it to the left by omega naught, and in the process it got divided by 2, but that's what it is here. Okay? So, if the original Fourier transform looked like this, which would be more or less typical of what gets transmitted, so some kind of low frequency signal, if it's speech or things don't go to very high frequencies. Okay? So this is my S of omega, and it has an amplitude, let's say A. The peak amplitude is A at 0 frequency. Okay? What happened was, after the multiplication with cosine omega naught t, what happened was we took it, divided it by 2, and shifted it to the right by the carrier frequency omega naught. So we put it now like this. This is omega naught, and the peak amplitude of this is A over 2. Okay? So this shows you 1/2 S omega minus omega naught. In a different color, I'll show you the other part. The second part is again half, but you shift it to the left, right? So that will be centered at negative omega 0. Again, the same amplitude. So this gives you 1 over 2 S omega plus omega naught. Okay? So that's all that happened when I multiplied my signal with a cosine. So why? Yes. That's a big S. I don't know, that's a big name, but yeah, it's capital S. They both are. I mean, everything there is capital. Okay. Anyway, so why are we doing this? Well, I can change this carrier frequency and add another station in there, right? We have all the frequencies available to us. Not anymore, of course, but just imagine when we
radio will be nothing, right? So I can have another station, somebody else doing some talk, and change the carrier frequency, apply a different carrier frequency, and their talk, whatever it is, can go in here. And somebody else's can go in here, right? That's basically what the different channels are that you get on your radio. Okay? Alright, so that's the benefit. Different carrier frequencies, shift things to different places in the spectrum. That way you can fully use the spectrum to make everybody happy. So what happens on the receiver end? Now you're in your car, and that signal, which is the multiplication, arrived. So what do? Well, I take that signal. I think I called that R in the note, but I didn't call it anything here. So yeah, we call this R of t. R of t, and so what you have here is R of omega. Okay. So R of t comes, okay, and this is the demodulation side. So what we do here is we multiply it again by cosine omega 0 t. It happened once on the sender end, why not do it on the receiver end too, right? And then you get a signal, let's call it G of t. Now let's see what G of t looks like in the frequency domain. Now you know, of course, I don't need to do this again. I know what happened to S when I did the same operation. It got shifted to the right, left, divided by 2. Same thing will happen to R, right? So G of omega, if I make a sketch here, G of omega is going to have two copies. One will be this R that you see at the top, shifted to the right by omega naught and divided by 2. What does that look like? Well, it has two domes, right? The one that's centered at negative omega naught will shift to 0. Okay? And then the one that was at omega naught gets shifted to true omega naught, right? And in the process, the amplitudes get divided by 2 again, so they become A over 4. Okay, so that's for this part, right? That's for this. Now, what happens to the other dome that was centered at omega naught? Oh, I'm sorry. I did that already, so I missed my color code now. Yes. Okay. I'm going to color this orange. Okay, so you know where it came from, okay? And then I have to take the same thing and shift it to the left this time. So the orange guy this time will go to here, this one, and then that guy will go to negative 2 omega naught, and then have amplitude A over 4. But now what I have at the center, omega naught, is two copies added together, right? So they add up, and instead of A over 4, I get A over 2. Okay? So G of t, after the multiplication with cosine again, will have this spectrum. The good news is that it actually contains the original signal, which is located at the right frequency, right? It's centered at omega equal to 0. It's this part, right? This part. This is basically what I had sent. But it now has replicas at 2 omega naught and negative 2 omega naught. How do I get rid of them? Or just low pass. Just, if I get rid of the higher frequencies, I'm done, right? So what I can do is do a low pass filter, perhaps with a cutoff frequency of omega naught. Okay. So this is the low pass filter frequency response. Okay. And if the amplitude of that is 2,
that means you recover perfectly after the low pass operation. You recover perfectly the signal that was sent. With now gain also fixes the reduction by division by 2, so I get the same thing as S of omega. So these two will match. Okay, so basically the receiver end has to do this multiplication, and also it has to do a low pass filter. And then you recover the signal. That's how AM works. The only difficulty is that the low pass filter that I pictured here is an ideal one, and we'll see shortly that ideal filters are really ideal and they can be ideal. So, yes. Yeah, that's what you're doing when you're jiggling the thing, right? You're shifting it, and then at every shifted frequency, you're demodulating, you're receiving something else, right? So if there was somebody else, if there's a separate station here, right? And if I increase this frequency here, then I'm going to be tuned to that. I'll be moving that to the center, and low pass filtering will eliminate everything else, and that's how I receive that. It sounds weird because that's not going to be perfect. That's going to be like something plus something. Okay? Yes. I said if you make the gain of your low pass filter to be 2, you can correct for that. The gain in this case is just volume. That doesn't matter, right? I mean, it's an amplifier. Yes. I don't see it as a combination. I mean, two things look similar, but other than that, I don't know, maybe you'll see more. Alright, we'll take a break and I'll leave you with a cool diagram that shows the US frequency allocation. Okay? You remember our frequency domain? It's full of stuff. Nothing is unused. Okay? So in fact, let's try to look for AM here. I think AM starts around 500 kilohertz. These are way too high. Yeah, so broadcasting AM radio. You see this? The little bluish thing. So it starts at 535 kilohertz, ends at 1600 kilohertz. 1605. Okay, so the different stations are usually spaced by 10 kilohertz, right? That gives each one of them a bandwidth of 5 kilohertz. So if you want to have a higher, more higher quality broadcast, forget it. You're stuck by that amount of frequency. Okay, you probably call a call center somewhere and they put you on hold and play some music they think they are entertaining with. So it's super annoying because over the telephone line the bandwidth is so low that you barely hear it, and you just hear some low frequency components of the actual music, and it's really disturbing. Anyway, so I'll put this on the courses along with the lecture notes. So it's kind of fun to look at this, and there's a ham radio club in our department. So if you like old school radio stuff, go for it. All right, let's take 5 minutes. And we'll continue that.
Oh well. In 10 minutes we'll have fresh batteries, and let's hope the quality is not too bad in the meantime. Alright, so this actually sounds stronger than the previous one. Okay, so one last property, and it's called the multiplication property. So we saw that if you take the convolution in time domain, we are doing a multiplication in the frequency domain. So if you believe this duality property, what would you predict about multiplying two things in time domain? Let's call them S of t and Q of t. What kind of Fourier transform would you expect from the product? Some kind of convolution. Those duality properties, again, are not perfect. There are factors that are different. Signs may switch. But essentially, you get some form of convolution in the frequency domain. And it looks like this. Now we are functions of omega. So remember when we were dealing with functions of time, we replaced t with tau, right? Something similar happens. Instead of omega, I'm going to put theta. And then the other signal will be omega minus theta. We'll integrate out over theta, and what comes out will be only a function of omega. Right? So why is this true? So to convince yourselves, what you can do is you can apply the synthesis equation to this. So the synthesis equation says take the function of omega, multiply it by e to the j omega t, and integrate, and divide by 2 pi. So if I integrate this over, it already is an integral over theta, but if I also integrate, multiply by e to the j omega t, and integrate over omega, then what I find is, I have to have another 1 over 2 pi, right? So that comes from the synthesis equation. And then there's already another 1 over 2 pi. But again, I'm going to switch the orders of integration. So I'm going to do 1 over 2 pi, integral over theta in the outer part, and omega in the inner part. That allows me to leave s of theta out, because that's with respect to theta. And what remains inside is integral over omega of p omega minus theta, e to the j omega t, d omega, right? And then we do d theta. I am forgetting a 1 over 2 pi somewhere. I think I can just sneak it in here, okay? So what does this remind you of? That looks like the synthesis equation, right? For what though? If that was just p of omega, I would get out of that p of t, right? But instead I have p of omega shifted by frequency theta, right? We just saw what shifting frequency in frequency means. It means multiplying by a sinusoidal in the time domain. That's how the AM works, right? So with the shift, this becomes really p of t, but multiplied by e to the j theta t from the modulation property, or just the previous property we discussed, right? Okay, so then things look easier. P of t can now be taken out. So 1 over 2 pi got bundled with this, so it's disappeared, right? So I have 1 over 2 pi p of t integral s of theta e to the j theta t, which came from this, d theta. And theta is just a dummy. It could just have as well have been omega, right? So that means what we have here looks like, including 1 over 2 pi, that looks like the synthesis equation for S. So that's S of t. So what we get is the product of P of t and S of t. Yes. The last property, 3 bars, perfect. So that was the last property we had to discuss. So from this point on, we will simply see some applications of these properties. So first of all, I want to go back to something we discussed a while back in the first couple of weeks, LTI systems. So I want to go and revisit those guys. They've been ignored for some time. Back to LTI systems. Alright, so in lecture 3, my notes say, that's one good thing about having notes, you can remember when things happen. In lecture 3, we saw that if we apply a sinusoidal e to the j omega t to an LTI system whose impulse response is h of t, what comes out is another e to the j omega t scaled by a number. And that number depends on what omega is. So we called it h of j omega and named it the frequency response. Okay? So the derivation was very simple. We basically took the convolution of e to the j omega t and h of t. So let me actually do it again because it's been a while and it's so simple. So the result, the output is the convolution of h and e to the j omega t. So I can just write e to the j omega t minus tau d tau, right? So that's the output when the input is e to the j omega t. Alright, so what we can do is we can split this as the product of e to the j omega t and e to the negative j omega tau. And of course this guy doesn't depend on tau, so why not take it out of the integral? We can just write e to the j omega t. What remains is h of tau e to the negative j omega tau d tau. Whatever this is, it only depends on omega, right? Because tau after integration will disappear. And this is what we call the frequency response, h of j omega. Yeah, that's where this came from. It was very simple. We just used the impulse response, the convolution property for LTI systems. There was nothing else to it. All right? But now you should recognize this here. What is this? That really is the Fourier transform of the impulse response, right? So the impulse response and frequency response are related by a Fourier transform. So that's important. You need to remember this. If you take the impulse response of an LTI system and take its Fourier transform, it's going to give you frequency response. Okay? Very important fact. Now, so far we used h of omega, x of omega, h of omega, whatever, for the Fourier transform, right? Whereas back then, we had insisted on keeping this j because we also did this for discrete time systems, and there it became h of e to the j omega. So we said, if we keep this j and e to the j, it will remind us whether this came from continuous time or discrete time. Also, we saw back then that I actually can apply e to the st with any arbitrary s, any complex s. It doesn't have to be purely imaginary like j omega. And what comes out from h of t is h of s e to the st, where this was defined as h of tau e to the negative tau s d tau, right? So that's a different thing. It's not e to the negative j omega tau, right? That also is a function, capital H, of one thing, right? So to be able to distinguish the frequency response, what we called that back then the system function or the transfer function, right? So to distinguish A, the frequency response from the transfer function, and B, the Fourier transform of a continuous time signal from the Fourier transform of a discrete time signal, which we will study next week, we're going to keep J. Sometimes when it's convenient, I might drop it when there's no room for confusion. But in places like this, I do want to keep the J. Okay? So don't let that confuse you. Essentially, it's a function of omega, whether I put a J next to it or not. All right. So now we know that what we called frequency response back then was really the Fourier transform of the impulse response. So now that we know this, we can do some fun examples. So we talked about filters, low-pass filters, and all that stuff, right? In fact, for the AM application, we need a low-pass filter. So an ideal low-pass filter would have a frequency response that looks like this. First of all, there's a cutoff frequency that you have in mind. Maybe you want to pass frequencies up to omega c, but reject those that come after that, right? So an ideal filter, low-pass filter, would be 0 beyond that point, and in between, it would be 1. Okay? So 1, and that I'm going to call h of j omega, frequency response of an ideal low-pass filter. But why is it ideal? We'll see in a second. So if this is the frequency response, what is the impulse response of that filter? It's the inverse Fourier transform, right? And what is that? Sinc, right? Last time we saw that sinc in time domain gives me a pulse in frequency domain, which this really is, right? And a pulse in the time domain gives me a sinc in frequency domain, right? So anyhow, from last lecture, I know that the corresponding inverse Fourier transform is a sinc. Looks like this. So this is our h of t. To be specific, when the cutoff frequency was pi, that was a perfect sinc. It was just sinc of t, nothing else, right? If we want to have an arbitrary omega c that differs from pi, we have to do the appropriate scaling property of Fourier transforms. When you do that, you just get omega c by pi sinc omega c by pi t. Okay? It's just a matter of scaling. No big deal. All right? So that is, if you want to build an ideal low-pass filter, that is how your system should respond to an impulse. Right? So what's wrong with this? What is so ideal about the ideal low-pass filter? Sharp cutoff is, yes, that's the ideal look, but in terms of implementation, what is the problem with h of t? What does that sharp cutoff translate to in time domain? It's not causal, right? There's all kinds of stuff before t equals to 0. How did I know the impulse was coming, right? So remember the causality test. Anything h of t has to do for negative time makes you non-causal. It has to be 0 for all negative t, right? So that makes it non-causal. So if you're doing that low-pass filter for your AM, radio, you obviously can't respond to a signal that hasn't arrived yet, right? So you have to build something causal in real life, right? So what do we do then? Can we try to get close to that? So what could be some alternatives? So what kind of approximations could I do? So I know that's not going to work, but maybe I can truncate h of t, right? Was that your idea? So how would you truncate? Okay. So the idea is shift it to the right, or let's change the order. Let's first cut off the tails. So I sometimes call these octopus functions, string functions. Right, so I can, and then I make silly jokes about, tails gone and things like that. Or what are they called? The tentacle. Yeah. Anyway, so what I can do is I can just zero out anything that comes after this, right? Just eliminate those. And there doesn't seem to be too much meat in those, on those edges. And then that's a finite duration h of t, still not causal. So that's just truncation. And then I can shift it to the right by this amount. So the result will be a new impulse response that sort of retained the essence of the octopus, right? And now it's causal. So what can we hope from this? Obviously, this is not going to give us these pretty rectangular frequencies, but what will it give us, right? So it turns out I can use all these properties we've been discussing today, put them to use to conclude what kind of distortion we're going to get in the frequency response of this, right? So let's go in order. So first thing we did here was truncate. The second thing was shift. And let's discuss the implications of each operation on the Fourier transform. Well, truncation really means obtain a new signal, h hat of t, by multiplying h of t with a window function, which this really is, w of t. Okay? So w of t is 1 when t is less than the period of truncation, let's call it t1, and 0 otherwise. Okay? So if I multiply my h, which is the octopus, with w, right? So the tail ends of the octopus will be gone, but the main center will be there, right? So that's the first thing. And then the second one is simply shift. How much will I shift? This point being negative t1. H hat has to move to the right by t1, right? So I'm basically defining these signals. First I define the truncated signal, I called it x hat. And then now the truncated and shifted signal, and let me call that, I don't know what, h bar of t. And that one is the final impulse response that I'm comfortable with because it's a causal one, right? So let's see what happened in the frequency domain while I was doing these things, right? So what happens in the first operation? I multiplied h with w. What happens in the frequency domain? It's a convolution. That was the last property we discussed, right? Multiply in time domain, you get convolution in the frequency domain. What am I multiplying? I'm multiplying a window function, w of t, with the ideal impulse response of an ideal filter, and that's what's happening. So basically, this will give us an h hat of omega, or let's put j omega. I said I'm going to put j, start doing j's, which will be 1 over 2 pi. It's not very nice notation, but it really is the convolution of h itself with w of omega, where w is the Fourier transform of the window function, right? So the window function, look at the window function. It itself is a pulse, right? So what is the Fourier transform of this window function? It's another sink, right? So h of omega is the ideal response. It goes from negative cutoff to positive cutoff. And this guy is itself a sink, but now in the frequency domain, right? So what is the convolution in the frequency domain of a pulse, which is the ideal filter response, with a sink? Well, you can think about that. I'm going to show you a picture because I don't think I can really draw a neat picture here. So for the notes, I made an effort. Lecture 7. Don't see anything? You do see something. Okay, so what's happening is here. Okay, so these are the things I just showed you. Window function multiplied with h, the truncated thing, right? So the convolution, multiplication in time is convolution of frequency. That means we are taking a convolution of the ideal h, which is that pulse, with the octopus, which is w. So let's say that h stays put and octopus gets flipped and dragged, right? So we have to use the dummy theta here doing the convolution. So we flip it and we drag it by little omega. Okay? And then what happens when you're doing convolution? Exam is in 2 weeks, so you better know your convolution. So what am I doing now? So I have to multiply the 2 and integrate over omega, over theta, sorry. And because that integration depends on theta, omega, which is that fixed parameter there, this gives you a function of omega, right? But just look at it qualitatively, right? So when the octopus is sort of in the middle of that window, right, the integral may change a little as I slide the octopus to the right, because the tails are leaving from one side, but some others are entering from the other side. So you can expect a little bit of wiggle, right? When little omega is, close to 0 or away from the edges, right? But as little omega comes closer to the edges, so imagine this picture with little omega, the center of the octopus, coming close to omega c. Now you're losing big chunks of the tentacles, right? And the area will start changing significantly, right? Now imagine omega has long passed omega c. What is left to integrate? Whatever tail is left in the, or you don't call it tail, but anyway, whatever tentacle is left inside the orange thing, that's what I'm integrating. They are going to be small numbers. And as I move omega further, it will get smaller, it will be a little wiggly because things are, the integral will change, right? So, and here is the result of the convolution. I really think it's very informative to think about, it reinforces your understanding of convolution in the first place, and also gives you a lot of intuition about these types of things. So, to see that the convolution operation illustrated at the top will result in the blue curve. Okay? That's basically what I was discussing, right? So this is the blue curve at the bottom, not the one at the very bottom. This bottom, okay? This shows you the result of the integration when you do the convolution, right? It depends on omega. As omega comes close to omega c, there is a huge, sharp change from being close to 1 to being close to 0. Okay? So I love this particular convolution. This is very pleasant somehow. And what happens if I take a longer window w of t? Remember it went from negative t1 to positive t1? What if I made that longer? What happens to this Fourier transform? If I stretch it, Fourier transform will compress. So the octopus will be skinnier, right? Or actually taller but skinnier, right? So therefore, when I do this convolution, that transition here will be sharper, right? It will move more smoothly and more quickly from one side to the other. Okay? So that means, so basically this is, after the truncation, the actual frequency response I'm getting, h hat. It's sort of close to the ideal one, but it's also different, which it should be because it came from a truncation. It gets sharper if the truncation allows a bigger window. Alright, so please look at the notes, make sure you understand this, okay? If your instructor is obsessed about something, you'll see it in some exam somewhere. inevitable. All right. So that was the truncation part. The next part is the shift. So what does shift do? So what the shift does is h bar of omega will look like what? If you shift in time, what happens in frequency? The answer is not much happens, okay? You retain the original h hat in this case of omega, but it gets multiplied by j omega, the amount of shift, which is T1, right? This guy. Okay? So the good news is, if you're only interested in the magnitude of h bar, that is the magnitude of e to the negative j omega T1 times the magnitude of h hat of omega, and the magnitude of e to the negative j omega T1 here is 1. So that means the magnitude looks the same. So whatever I showed you here for h hat of j omega, that's also, of course, magnitude means the negative sides have to be folded to become positive. But magnitude-wise, it will look just like this. The only difference is that the phase that emerged from this operation, from this delay, right? So the phase will be different. The phase, remember, when you have two complex numbers multiplied, their phases add up, right? So that means the phase of h bar is the phase of h hat plus the phase of this guy. And that phase is negative omega T1. That's basically the amount of delay you have to live with, right? So to make this implementable as a causal thing, you had to live with some delay, right? So you wait a little bit, or truncate and then wait, right? And you have to pay for the wait in terms of phase, okay? So delays don't change the magnitudes in the frequency domain, it only changes phase. So phase is something you should associate with timing, okay? Delays are due to phase in the frequency domain. Okay, so that's how you go from an ideal to a non-ideal filter. So everything's in the notes. All right, let's talk a little more about LTI systems. So in homework 1, which is it due today? Yeah, so I'm sure you all did it, right? You're not going to wait until 10 p.m. Okay, so there I asked you to look at constant coefficient difference equations and argue that these are LTI systems. A similar argument that is not in the homework holds for constant coefficient differential equations, and those define continuous time, linear time invariant systems if the system starts at rest, right? The outputs are 0 before any input arrives. So the general form of a constant coefficient differential equation representation of an LTI system is like this. The kth derivative of the output gets multiplied by a coefficient a sub k, and you add those up from k0 to n. So this basically means a0 y of t plus a1 dy dt, and the highest powered term is an, the highest derivative term is d to the ny dt to the n, right? Okay, so that's the left-hand side of the equation. The right-hand side is the effect of the input, and that's usually described by similar terms. Again, an index k goes from 0 to m this time. b sub k, kth derivative of the input, d to the k. Alright? So given an LTI system that starts at rest, so is LTI, defined by this differential equation, I might ask you, what is the frequency response of this? Right? How do you answer that question? one thing you can do is first you have to find out what the impulse response is and then take the Fourier transform. But dealing with impulses in differential equations, that's not going to be pretty, so let's not do it that way. There's a more direct way. In fact, in the homework, I told you to do just that. There was an RC circuit example, right? I told you that, look, if this is LTI, you know that when I take the input x of t to be e to the j omega t, the output is, just from the property of convolutions, as we've shown back in lecture 3, y of t is going to be some h of j omega times e to the j omega t, right? I said substitute those in the differential equation, and you're going to get a bunch of expressions, but there will be an h of j omega hiding in there, and you can find out what that is. Okay? For example, if you have a first order differential equation, let's say tau times dy dt plus y of t equals x of t. Okay? So that has the form above, but very simple. What is capital N? How many derivatives are needed for the output? Only one. For the input? None. Right? And what are the coefficients? A1, which is the coefficient of the derivative of y, is tau. A0, which is the coefficient of y, is 1. And B0, which is the coefficient of x, is also 1. Right? So this is all coming close to solving your homework problem, but anyway, it was an easy problem, so I don't worry about it. So if I just substitute this here and substitute that for y in both equations, then I should be able to pull out an expression for h of j omega, right? So let's do that. So tau dy dt means I look at this, take the derivative, right? What is the derivative of this with respect to time? Tau j omega e to the j omega t h of j omega. That's the first term, so we've taken care of this term. Plus y itself, so that is e to the j omega t h of j omega. And the right hand side is simply x, and that is e to the j omega t. So cancel e to the j omega t from all sides. A 1 is left here. So that means, and then factor out h of j omega, so you can write 1 plus j omega, j tau omega, or however you want to write it, times h of j omega is 1. And that already gives me h of j omega 1 over 1 plus j omega tau. Okay? So that's the frequency response. You don't have to do anything other than substitute things, right? In fact, if I ask you about the impulse response now, you can go backwards from this expression. This expression was easy to find. I can go backwards from here to figure out what h of t is. Can you do that? Let's make it look a little prettier first, so that I want to make it look like something I know, and that is 1 over a plus j omega, right? Because I know this is associated with e to the negative at ut. So let's try to use this, but I want to make it look that way first. So if I divide both the numerator and the denominator by tau, I'm going to get 1 over tau by 1 over tau plus j omega. Do you agree? So then this means 1 over tau plays the role of a, right? And I have a factor of 1 over tau that I did not have here, so that will have to go as a factor to the function of time itself. So I'm going to have e to the negative t by tau u of t. Okay, and there you go. This is your h of t.
Yeah, I'm not doing a good job organizing this page, but h of t is this guy. Right?
Right, questions?
Okay, so alternatively, instead of substituting x equals e to the j omega t and substituting y equals h times e to the j omega t, we could have just taken the Fourier transforms of both sides of the differential equation. Right? What is the Fourier transform of this guy? I realize this page has become a mess, but the notes are not a mess, they are very clean. So tell me, what is the, if the Fourier transform of y of t is y, capital Y of j omega, what can you tell me about this? Derivative property. J omega, but raised to power n times y of j omega, right? What about this? This is simply a1 times j omega, right? So everything on the left, if I take the Fourier transforms of both sides and use the linearity property of Fourier transforms, I can take out the factors, right? And then each kth term has j omega to the power k multiplied by ak, and it has a factor of y j omega, right? So take Fourier transform of both sides of differential equation, and what you're going to get is sum over ak j omega to power k times y of j omega k0 to n. But since everyone has that factor y, I can just factor y out. And on the right hand side, you'll find k0 to m b sub k j omega to power k times x of j omega, right? So we are talking about linear time invariant systems. So if I have input x of t, what comes out is y of t, that is h convolution with x of t. And from the multiplication property of convolution, I know that this can be written as, in the frequency domain, I can write this as what? I'll ask you. H of j omega times x of j omega, right? So really, h of j omega is y of j omega divided by x of j omega, which I can find using this expression. Y by x would be what I see here divided by this, right? So bk k omega to power k k0 to m by k0 to n ak j omega to power k, right? So this is a general recipe for finding the the frequency response of an LTI system defined by a differential equation of this form. Okay? So if your differential equation is this, then your frequency response is equal to this rational term. Right? So we already saw a first order example, but that easily generalizes to any order system. I'm not going to give you a circuit example because that would be the solution of your homework one. Anyway, we did 90% of it. So let's talk about, so this is only, the RC circuit is only a first order circuit. The highest order derivative involved is just the first derivative, right? So let's look at a second order system as a special case, and we'll continually come back to this in this course. So let's assume there are no derivatives of the input, so we'll take a specific form. So d square y dt square. Why did I start with this? second derivative because it's a second order system. Order means the highest derivative of the output involved. All right, plus a1 y of t plus, I'm sorry, a1 dy dt plus a0 y of t equals x of t. Okay, actually I'm going to put an a0 here and don't question that now. So b0 happens to be the same as a0. Okay, just I'll normalize it so I don't have to deal with that coefficient separately. Okay, so that way the only independent coefficients are the ones that I see on the left hand side, a1 and a0. All right. So what is the Fourier transform of, what is the frequency response? From what I've seen above, h of j omega is a0 by, tell me, well, because b0 is a0. Okay, a0 plus a1 j omega plus j omega squared, right? All you have to do is apply this formula here, right? This one. Okay? So the problem with this representation is, if you want to know what this looks like as a function of omega, of course it's complex valued, but you can look at the magnitude, etc. If you want to know what it looks like, how it changes with a0 and a1, it's a very complicated dependency on a0 and a1, right? It will change like crazy as you change a0 and a1, right? So for that reason, people prefer a different parameterization of a0 and a1. Instead of using a0 and a1 as the parameters, they are going to use two other variables, and they are unfortunately Greek letters, xi or zeta, I don't know what it is, and omega n. Right? So they have some physically motivated names. Zeta is sometimes called the damping ratio, and omega n is called the natural frequency. We'll talk about those physical things later. But for now, just believe me that instead of using a0 and a1 as my parameters, if I use zeta and omega n, where a0 is omega n squared, and a1 is 2 zeta omega n, somehow the frequency response will look nicer. At least the role of zeta and omega n will be very clear in how the frequency response changes. Okay? So can you live with this reparameterization? If I gave it to you in this form, you can find an omega n and zeta, right? No big deal. Right? You can go back and forth. You have two equations to solve. a0 equals omega n squared, and a1 equals 2 zeta omega n, right? If I give you a0 and a1, you find omega n from the square root of a0, substitute it here, and solve for zeta, and you're done, right? Likewise, if I give you omega n and zeta, you just substitute these here, you get a0, a1. So they're equivalent representations, only the zeta and omega n representation will look nicer, and you'll see in a second why. So let me do these substitutions in here. Okay, I'm going to make some room here. So this is 2 zeta omega n, and this is omega n squared. And I'm going to erase this stuff so I can squeeze the expression here. Okay, so what happens to this? It becomes omega n squared by j omega squared plus 2 times zeta times omega n j omega plus omega n squared. Why is this prettier? It's not. But it will be if I divide both the numerator and denominator by omega n squared. It becomes 1 by j omega over omega n squared plus 2 zeta j omega by omega n. Can you even see what I'm writing? Plus 1. Okay? So, whatever you can see there, if you can see anything at all, something nice has happened without you noticing probably.
Omega always appears in the form of omega by omega n. So how would omega, how would this frequency response change as I change my omega n? Omega n appears nowhere else. It just, wherever there's an omega, it is divided by omega n. So if I choose an omega n that's 10 times bigger, what happens? I kind of strange that thing, right? Okay? So it basically becomes this, stretching factor. It doesn't change the shape of the frequency response. It just changes the, it either compresses or stretches it. All right? So that's why we prefer this notation. So really the shape is determined by zeta alone. The role of omega n is simply to compress or stretch. Let me just show you those figures and I'll let you go. So here is the frequency response of the second order system for various choices of zeta, right? So it does not depend on omega n. It does because I told you omega n stretches or compresses. For that reason, we've actually factored omega n into the frequency axis. So if I choose a bigger omega n, I've actually stretched it, right? But the general shape other than that does not depend on omega n. It only depends on zeta. If I choose a small zeta, the frequency response, instead of nice and smoothly decaying as omega goes to infinity and acting like a nice low-pass filter, if zeta is not big enough, below a critical value like zeta equals 0.1, 0.2, etc., it's going to go up first. Look at this jump. So there is a frequency range where your system is hypersensitive, right? So if you excite that system with that frequency, I'm just overreacting to it. I go crazy. I just respond, I return the oscillation in multiples, right? That phenomenon is called, have you heard anything like that? It's called resonance. Okay, so this is a resonance phenomenon that you're seeing here. And that happens if the zeta factor is small. There's a critical value that I'll put in the notes where it comes from. It's very simple. When zeta is around 0.7, that starts happening. If zeta is bigger than that, you have a nice and monotonic decay in frequency, so you look like a nice low-pass filter. But zeta is smaller than 0.7, you start getting these peaks, and those peaks get really, really, really big as zeta gets smaller, and you get horrible resonances. Okay, that's why soldiers are told not to march when they are crossing a bridge, for example. A bridge has this resonance frequency, you don't want to excite that, right? For obvious reasons. And there are all kinds of cool examples of, not cool and scary examples of resonance as well. Maybe one day I'll play you something. Not today. Alright, so we'll stop here. See you on Tuesday.